to the webinar, and we're going to get started in just a minute. I'm going to give this, well, actually we're already a minute past, so we're going to go ahead and get going. Hi, welcome. My name is Kathy Hoverman, and as usual, I'm moderating today's webinar from the Joint Committee on Fisheries, Engineering, and Science, a collaboration of ASCE's Environmental and Water Resources Institute and AFS's Bioengineering section. You may hear us refer to the committee as the Joint Committee. We're talking about that whole long name. So welcome. So the Joint Committee is more than just webinars. If you're interested in being a part of the Joint Committee in any way or learning more about it, you can check us out on our website or also reach out to anyone on our executive committee listed here. This webinar series began in 2015 to share information on aquatic organism passage, dam removal, fisheries improvement, community and stakeholder engagement, and related riverine topics all around fish passage. Since our inception, we've provided free quarterly webinars, with today being the second in the 2026 series. This webinar is being recorded and will be available on our YouTube channel. And you can find all of our past up to at least about 5 years ago on this same YouTube channel. So go ahead and search it up and enjoy all the webinars. Just a few other things. We have some dam removal training resources on our website. Please check that stuff out. It's great, especially if you are new to dam removal, or you have an employee that might be new to it or wanting to learn more about it. If you yourself don't know a ton and are also learning, these are great resources to help at a variety of different levels to get into some of that training resources and also kind of like best practices. You can also find us on LinkedIn as a way to stay connected and just be a part of conversations, start conversations, ask questions to colleagues around the world. The webinar series is put together through a team of us that are the webinar task committee. So always big thanks to them. And we're excited to bring you this next one. And our next speaker will be in September, which we're still working out the details on that. So I'm not gonna give that away quite yet. And I will say our speaker for today, Sam Prentice, he's actually recent member to the Joint Committee, and looks like he'll be joining us on our webinar task committee. So we're excited to have him. But for you all today, for this presentation, a little background: Sam is a licensed civil engineer, works for GEI Consultants out of Marquette, Michigan. Sam's worked for GEI for 11 years as part of the collaborative team specializing in dam removal, stream restoration, and fish passage projects. His responsibilities have included grant writing, data collection, hydraulic modeling, permitting, design, and construction oversight. So I like that, soup to nuts. Sam is an active member of the Michigan chapter of American Fisheries Society, currently serves as the Rivers and Streams Corridor for the chapter. Outside of the office, Sam enjoys recreating in the greater Marquette area and along the south shore of Lake Superior. So with that, I'm going to turn it over to Sam and look forward to hearing more about this project, which I first learned about at the National Stream Restoration Conference back in 2023. So we're excited to see the progress. So Sam, please take it away.
Thanks, Kathy. Good afternoon to folks on the East Coast, Eastern Time Zone. Good morning to folks in the Central Time Zone and our neighbors to the west. Like Kathy mentioned, this is a project that GEI and others have been involved in for a couple of different years. It's a pretty neat project, so happy to share it with everybody. Just doing a screen check, Kathy. Can you see the presentation?
Yep, looks good.
Cool. All right, so I get an hour. I know I can't talk the whole hour. We've got to stop for questions at the end, but this is pretty neat. When I just presented on this at the International Fish Conference, I only had 15 minutes. So for folks that know me, I really like to talk about this. So our agenda, we'll do a brief history lesson. I'll go through some of the design that we did, the freshwater mussel survey that was done pre-construction, Some of the materials that were used, our approach with construction, kind of currently we're trying to do some fundraising and thinking about monitoring for fish passage, and then we'll end with the Q&A. So for folks that are not familiar with the state of Michigan and Michigan's Upper Peninsula, we're almost into Canada. We're on that south shore of Lake Superior, and this is just an older geologic map of the entire country. So into Michigan's Upper Peninsula, the copper rush happened in the mid-1800s, 1840s. If you guys are familiar with the California gold rush, the copper rush itself was like 10 times the amount of money made from that shorter gold rush in California. And then this project, the Republic project, that was actually extraction of iron ore from the earth. And so you have a lot of minerals that were pulled out of Michigan's Upper Peninsula, certainly into Wisconsin and the Minnesota Iron Range as well. But it's just a really cool part of this project, and it does actually have ties to the work that we were doing more recently. So you'll see the little note there called Republic District. That is the Republic Dam and the project site that we'll be talking about today. There was a mine opened in that area in 1872, and then one of the dams that we just removed in 2024 was actually original to that mine. So that was built in 1876. This is a little ortho mosaic just from Google Earth. So the original mine operated from 1872 through 1920. There was a pretty long hiatus here and at many of the other iron mines in the Upper Peninsula. The pelletization for making taconite, which is kind of these marble-sized pieces of ore, was developed in the early to mid 1900s, and so that was the reason for that reopening from 1950s through 1982. The mine closed for good in 1982 and has not reopened. So I think the context is important. We're here to talk about dam removals and fish passage and rapids, but the community here really it was literally born out of mining in the 1800s and really hasn't known anything else since then. When we started working with our client, they are now trying to change the way that they look at making money and inviting tourism, specifically outdoor recreation tourism, into their community. So I thought, it was kind of important to share some of this historical context before we got into the nuts and bolts of the project. So that this lake on kind of the middle part of the screen, that is actually the old open pit mine right in here. So that's a 600-foot deep open pit mine that was flooded. And then any of the high value ore was taken out either down to Green Bay or to Marquette to load onto ore boats to take through the Great Lakes and out to the ocean. But any of that waste rock was actually piled up here. So there's this massive 300-foot tall waste rock pile that will come into play later as we talk about lots of rock that needs to be moved around. And the Michigamme River itself, it flows kind of down and to the right. We'll be focused on this area for the project. This does flow down into the Menominee River, which forms the border between Michigan's Upper Peninsula and Wisconsin, and then eventually out to Lake Michigan. So this is that timber crib I was talking about from 1876. So that old open pit mine is behind the trees here. There's a former powerhouse intake canal we'll talk about later. But yeah, this was the original timber crib structure that was built in 1876 and removed in 2024. And then this was a more modern dam. I use that term loosely, but this was built just downstream of that timber crib and built in 1915. There's three 12-foot wide vertical steel gates that were raised and lowered to moderate the water levels, either into the powerhouse when power generating was happening for the mine, or in more recent years for regulating the basin elevations. Some more recent history, 2010 to present, like I mentioned, Republic is trying to reinvest in the outdoor tourism industry with a pretty low likelihood of the mine reopening. GEI did a couple of different dam inspections. From those inspections, there were multiple repairs recommended on the dam itself. From that point, really into 2021, there was improper operation of those gates. They were raising and lowering the water very quickly, and so that had impacts to the riparian wetlands, obviously to fish, mussels, other stranded organisms that could be stranded. And so there was a lot of concern for the environmental health around the basin and for the river. And so that's really when we started to get involved. We were trying to think of these ideas of how do we maintain some water level, but also allow for fish passage. And so that was when I got involved in 2018. And like Kathy said in my bio, I kind of, for this project, did grant writing, data collection, design, construction oversight, like kind of everything from beginning to end. So now that we're through the history, just want to talk a little bit about the design approach on the project. So the goals that we were given working with the client was to remove those two dams, build a passive structure that would maintain a water level that they wanted within the river basin, and then even to support some of the infrastructure upstream. There's a highway bridge crossing pretty far upstream where a lot of boats were bottoming out with the gates open on the old dam and lower water levels. So it wasn't really just to drive the economy. There was also some infrastructure concerns with having those lower water levels in the summer. Providing fish passage for warm water species, and I'll talk later about what the differences are between the swimming capabilities with warm and cold water species. Maintain or lower that 100-year flood elevation, reduce long-term risk and maintenance, and then again, improving those recreational opportunities. So the design we landed on was a rock rapids. We probably went through 4 or 5 different options for a couple of different years on, what do we build here? And for those not familiar with what a rock rapids is, it is an alternative to full dam removal. So if we removed those 2 dams, it would have been a much cheaper and faster process. But then the client would have had no way of maintaining a minimum water surface upstream in the basin. And so when I say basin, it's the river up here and to the right. And it's a revised design from a continuous rock ramp. So with a rock ramp, you could just see a big wedge of rock through here with no pools, no gaps in the boulders. And so this is a much more intricate design that actually keys on the burst swimming capabilities of warm water fish. And these boulder weirs are set up in a sense where we're only dropping 1/2 foot to 0.6 feet across each of those weirs to step down this 15-foot head differential. And then another really important design aspect is these resting pools. So below each set of boulder weirs, we have at least 1 and sometimes 3 resting pools for fish to recover and then to continue to move upstream. And then one last thing, these structures could be built directly onto or adjacent to an existing dam structure. In this case, both dams were fully removed, but we have another project we're working on right now where the dam itself is staying in place, and then we're adding in the rapids right around that existing concrete dam. So I wanted to give Luther a shout out here. So Dr. Luther Adland, he's retired from the Minnesota DNR. He was very involved in this design. He's shared decades of data and has built over 100 rock rapids. On the slide here is his book when he was with the Minnesota DNR from 2010. And so a lot of these concepts that I'm sharing were developed by Luther, and he has continued to revise that information and update the design criteria. So definitely recommend checking out his book to learn a little bit more about these structures. So the way that these work, most warm water fish really don't have any jumping capabilities. So these are not the salmon in Alaska that are jumping over natural rapids. The warm water species do need to be able to move through the water to be able to traverse the rapids and move upstream. In addition to not being able to jump, they're typically weaker swimmers than the cold water species. And so the image here is showing kind of above and below water look at these gaps that were purposely left in between the boulders. And so the fish are able to hide behind the boulders and then shoot up through using their burst speed capabilities. And then as soon as they are upstream of that set of boulders, they can then go to the resting pool or hide behind the second set of boulders to recover their energy and move up through the structure. And I think one of the reasons I wanted to talk a little bit about the rock rapids versus the rock ramp is we're really trying to build up that hydraulic complexity with the rock rapids. So the difference between the gaps in the boulders, the difference in the boulders themselves, and then how the hydraulics are interacting with that really does set up that diversity. And then also in those resting pools, we're seeing different fish species. The velocities there are near zero. And so it's a great spot for the fish to be able to rest and regain their energy to then continue moving upstream. And then another piece of the design that we had to think about was having a terraced cross section. So we have 3 levels here. If you looked at the cross section, we have a thalweg at the lowest elevation, a low terrace, which is a 6-inch rise, and then a high terrace, which is another 6-inch rise. And so what that allows us to do at higher flood flows, like what's being shown in this video, is you have very calm water along the edges of the banks to reduce those erosive forces, but we still have some pretty violent and turbulent water that's occupying the thalweg and the low terrace toward the middle of the channel. So the design approach was to remove the dams that we talked about, add rock fill at the upstream end close to that 1492 target elevation, size the upstream weir crest so that we were either meeting or lowering that 100-year flood elevation, spread the fall, the 10-foot fall from the dam, and then another additional 3.7 feet of fall over this entire structure to try to hit a 2% slope, maximize fish passage, build in these sine wave weirs. And so when I say sine wave, we have kind of this convex and concave form and plan view, and that really helps to concentrate flows down into the resting pools to maybe move sediment out that's accumulated there. But it also helps with the hydraulic cues and attraction flow for fish. And so they're able to move through the wider gaps and know which way is upstream as they're making their way through each of the sine wave rows of weir boulders. Excavate the resting pools in between the weirs and then do the terraced cross section like I previously mentioned. So the criteria for this, we did have Luther on our team, which was fantastic, but we also used some of the fish biologists that we have on staff at GEI, and we collaborated very closely with the Michigan DNR local fish biologist. And so the DNR had done a study in 2018 in the basin. We knew the species that were occupying the Michigamme River. And from there, we were thinking about what depth of water those fish need, when are they trying to pass, what is the discharge, what time of year are they trying to move through, what are the velocities, are they moving voluntarily, are they being attracted to the rapids itself, thinking about flow condition, whether it's sub or supercritical flow, looking at the different gap widths to allow different sizes of fish and different species through, the roughness, slope, shear, and then also the vertical drops across each of those boulder weirs. So here's, I guess, kind of a simplified table of each of those design criteria that we're looking at. So the head loss per weir, I like to think of it for easy math as half a foot. 0.6 is actually the design criteria that was used, but that is related to the velocity, that longitudinal slope, keeping it at 2% or less, varying the gaps between 6 inches and 3 feet, trying to maintain a depth within those gaps of 2 feet. The resting pools being at least 5.7 feet, but ideally greater than that. And then also these shallower pools in between those deep resting pools, making sure we have enough depth there so that fish have the availability of moving laterally from the channel as they're trying to move more toward the edges during high flows. So for the head loss, the reason that 0.6 foot drop is so important is you would need to do some math, but it basically relates back to that velocity. So if you look at the graph, that 0.6 is on the x-axis. If we run over to the velocity on the y-axis, we'd be looking at roughly a 6 foot per second velocity through the rapids. And you can see with that yellow line, if we increased that head loss, we would just be going higher and higher with velocities. And so with a lot of the work that Luther has done and the data he's collected on fish passage, he has adjusted that head loss number lower and higher. And then as he's collecting more and more data and assessing the success, he's kind of settled in on this half a foot, 0.6 foot number that we use for the Republic design. So again, with some of Luther's work, he started out with using a steeper slope, a 5% slope, built a bunch of these, studied the fish communities, studied the passage capabilities, and then again, reduced that slope down closer to 2% for the ideal way of maximizing fish species and age classes for the warm water communities. And then this was a pretty neat thing. When we were working with the client, we were able to get our hands on the original surveyor's notes for Republic. And so that highlighted section translates to several rapids on the river with sufficient fall for driving machinery, 18 feet of fall in a distance of 14 to 15 chains. And so a chain is a length of measurement. Converting that to feet, we were actually able to get very close to like what the natural fall was through this section of the river. So that was kind of a fun thing that Luther and I were able to do together. Here's some more of his data. And I think the key takeaway here is we have a bunch of different species, some of which were caught during that 2018 DNR survey. Others were used as surrogates, so similar. And this graphic is showing those different species and then their peak or sprint swimming capabilities. So this is what we're trying to use when they're shooting through those gaps in the boulders. And a roundabout way of thinking about this is that's typically 8 to 10 body lengths of the fish per second. Moving into a second graph, this would now be the prolonged swimming speeds, and these are much less. And so if you're thinking about a fish trying to make its way through a culvert, or if there's no refuge or resting pools, that would be closer to 1 to 4 body lengths per second. And so we took this data from Luther, we did some of our own work, and we started building out this list of all the different species in the Michigamme River, using surrogate species if we didn't have data for those. And then we came up with the depth limitations and velocity limitations. We also used work from others. So this is a Castro Santos paper that some may be familiar with. And this is actually looking at the fatigue time for fish. And so it's in the body lengths per second, but they're also measuring how quickly did those fish fatigue. So in this example, if you had a 6-inch walleye and they have a sprint speed of 15 body lengths per second, that would translate to 7.5 feet per second for their swimming performance for 2 seconds. And then if we think about this and apply it to the river, they would be able to swim at that velocity, the 7.5 feet per second for 2 seconds. But we really haven't accounted for the forces of the river itself. And so you have to do some subtraction there. In this example, I just used the assumption the river was moving at 3 feet per second. So the ground speed of that fish is really only 4.5 feet per second. You can kind of think of it as this treadmill phenomenon or infinity pool, I suppose, that if they aren't able to make any, they can't actually swim forward at the 7.5 feet per second. It's the net of the two. And then they only have the couple of seconds to do that. And so you would have to turn it in to a distance. And in this case, they would be able to travel 9 feet before becoming exhausted. And so most of the gaps in between those boulders are ranging from 3 feet to 5 feet, so much less than 9 feet. And we all know that biology is complex and the behavior can't be predicted exactly. But generally, you could see that if this fish needed to swim up through a 20-foot culvert with no refuge, they're probably not going to make it. But they had a pretty high likelihood of making it through these shorter gaps using their burst speeds. And then a additional complexity is just how close are they to the bottom of the river itself? Typically, that's where the roughness elements and the friction is greatest, and that means the velocity would be lowest. So the fish are innately using this to their advantage. They're hiding behind rocks. They're right at the bottom of the river. And so the takeaway from this slide is that the adult fish, just because of their size, especially for larger species, are going to have their noses further off the bottom where the velocities would be higher than if it was a young of year fish or a minnow, a smaller species, and they're able to get right down to the bottom of the river. So we took all of that fish data. We did build a pretty complex rapids surface in the Civil 3D and modeled each of the boulders and each gap, and then brought that into HEC-RAS 2D. The mesh size we used for the HEC-RAS model was much larger outside of the rapids just to save on runtime and file size. And then down in the rapids itself, we used a much finer mesh size, so a 2x2 mesh. And then we also aligned those break lines with the sine waves built into the model so we could better understand the modeling results. And so we looked at those different design criteria: velocities, depth, sub-supercritical, using the Froude number. And we did that at 4 different flows. The ones that we were most interested for fish passage was a summer low flow, an average daily flow, and then that bank full flow. The 100-year really was just looked at to make sure we weren't increasing that from what was there when the dam was in place. And so what's nice with this two-dimensional model is you can see when the velocities are high, the fish may actually want to move laterally. And so that's what this second slide is showing, is if you have a lot of hot red colors in the middle, maybe we're thinking the velocities are too high. We do have these resting pools and shallower pools that are connecting to those laterally, so the fish can actually hug the banks as they would naturally in the river. This is just a profile cut along the Thalweg, but you can see the geometry of the rapids in the maroon on the bottom, our 4 different flows, and then we did run one flow file with different time steps or different times that those flows would kick in to see what the depth was and to also look for that 0.6 head loss. So some of the limitations with modeling, you have to put good data in, and you also have to have an understanding of what results you're looking for. So that's why it is critical to be working with a team that understands fish behavior and their ability to pass and what their swimming capabilities are. As most of us know as engineers, Civil 3D is great for roads and other traditional civil projects. Not so great on river and complex rapid surfaces. So just knowing that going in, it's going to take some time to massage those tools to get the surface that we want for doing the hydraulic modeling. We did go ahead and choose to use a two-dimensional model for this. We did that knowing Luther had a lot of really good data. He knew how to interpret the model and help us on that end. You certainly could run a 3D model for this. You would also still need to understand what those results mean and if fish are able to move through the system. But that third dimension for this two-dimensional model is actually depth averaged. And so this is a little chart from Luther's book just showing how those velocities change with depth as you go from no depth, in this case, all the way up to a 1.8 foot depth. And that would be for boulder rapids, a box culvert, and then a natural gravel riffle. I think I'm getting a little low on time, so I'm gonna rip through the muscles to try to get down to some of the construction approach. So good during the permitting phase, permitting took a couple of years on this project because it was the first design done in this manner in Michigan. So it was very new to both the DNR staff and the Eagle staff that were reviewing the application. Total survey time was 77 hours. We found nearly 2,000 live mussels. 92% of them were found in these corners right by the old dam. And for those of you that aren't as familiar with this, these are native freshwater mussels. And so the objective here was to survey, find, and relocate them outside of the construction footprint. So these are, in this case, these are all giant floaters. They're about fist sized, and they embed themselves down into the sediment. And then this white part right here, that is actually the live mussel inside the shell that's opening and siphoning and filtering the water. So those were the conditions upstream of the dam on the top, downstream of the dam on the bottom, and then this is the substrate for both. Just looking at a mixture of gravel, sand, and boulders upstream, and then some of that downstream, but there was much more boulders downstream just because there is a natural rapids that we were trying to tie the project into. And then this is kind of an interesting slide. We only found giant floaters. The natural hosts for those, many of those were off of that list from the DNR for the fish that were surveyed in 2018. And then there's some lab evidence of different hosts for giant floaters, and then some non-specified host evidence with white sucker. So mussels were cleared out. We were able to move into construction. I'm going to talk about the materials here quickly and then move into the actual construction approach. So we had the old mine there, right? Talking about the history. This hill slope in the back is that 300-foot rock pile I was talking about. And so the contractor was able to process a lot of the material for this project right on site. And so we had three materials we were using. I'll refer to one as armor stone. So that's this much larger 8 to 30-inch material with a D50 of 18 inches. Chinking stone, so that should chink the gaps and fill the voids in the armor stone. So that was fines up to a 5-inch material. And then finally the weir boulder. So those were 36 inches in all dimensions. So the armor stone forms the base of the rapids. For folks that are familiar with rock sizing, we were using some traditional critical shear stress Army Corps calcs to get a D50 from that. If there were areas of the bed that were prone to scour, we were then using the rock thickness to be twice that calculated D50. Fortunately, the Michigamme River does have a lot of very large rock on the bottom of the channel, so we really didn't have to line the pools with that twice D50 thickness. But if you were working in a sand bed system, that would be a critical component of the design approach. That rock was sourced from the mine stockpile, like I'd already mentioned. And then we went through an interesting process to confirm that D50 by weight instead of by count. And so for that process, we had a loader bucket, or the contractor had a loader bucket that had a scale on it. They would move a sample over and take measurements on what that sample weight was in tons. And so that's what the readout from the loader is showing right here. We would walk through the pile with them and mark off anything that was smaller than that 18-inch D50. Those smaller pieces of rock would then go back in the loader bucket, and that weight would be collected in tons. And then in this case, because we took the stuff that was smaller than 18 inches, if that weight was less than half of the total sample weight, we would know that we met our D50 and the sample would pass. So the chinking stone, so that was the fines up to the 5-inch, that was layered in lifts with the armor stone to build out the base. It was also placed on the upstream side of the weirs to minimize seepage through the structure, and it also formed the top dressing at the crest of the structure. We did give a spec for this, and we did get close, but as you can see with the rainbow colors here on the gradation report, this was absolutely an iterative process. The contractor was well aware of that, and this was very much a performance spec, basically saying that we needed to make sure that seepage was minimized through the structure, and they would need to generate multiple mixes to get the recipe correct. And then finally, the weir boulders, those will get embedded halfway into that armor and chinking stone mix. This is where the fish are swimming through, so they're swimming through the gaps in the boulders. this is the way that you control that critical measurement of head loss, is adding in those boulders and then adjusting the gaps. Minimum density for our spec was 165. If we remember back to the history lesson, this whole area had very high iron content. These waste rocks still have iron in them. It just at the time was not profitable to break them and process the iron. So the rock here had a much greater density than our spec. It was 270 pounds per cubic foot in some instances. And then in the field, what we were doing was measuring those dimensions. If we were 36 inches in all dimensions, we'd mark it with a dot. If it failed, we would mark that with an X. So moving into the construction approach. So this was a local contractor. Most of their work is producing aggregate and other materials. They do some earthwork as well, but they had no previous experience building one of these rapids. They owned that old mine property and the stockpile of material that we've talked about. They were able to complete the work in one season. So they started in May and ended in November of 2024. Their fee was right around $2 million to do that work. This was supported through grant funding from the DNR Fisheries Habitat Grant, the State of Michigan's Eagle Risk Reduction Grant, and then for local matching funds, Republic, our client, did have a local millage passed to support the grant funding. In this top picture here, you're basically seeing their construction crew. They had a foreman, an operator, a couple people that ran loaders, and a truck driver. So it was a pretty small crew. They did have GPS machine control for replacing all the boulders, digging out all the pools, and some of the side slope tie-ins. And then they were manually going through and measuring the gaps, and then also that head loss across each of the rows of boulders. So construction sequence, they removed both of the dams, processed the material, built the crest at the upstream end, layered in that chinking stone to minimize the seepage. And then they basically worked from upstream to downstream in rows of 3 for those boulder weirs. And then as they got downstream of the former dam and they were going further and further down, they did need to tie in to the side slope where those vertical abutments were for the old dam walls. So they began cutting that east bank, adjusting the weirs to meet that 0.6 head loss requirement. This intake canal was also filled. That was more of a, I guess on this project, maybe a geotechnical seepage concern. The rapids itself is great at handling water that's coming downstream, not so great at handling lateral flows. And so there was a concern that this berm would overtop at higher flows, hit the boulders laterally, and that could lead to a potential failure. So the decision was made to fill this intake canal, raise that above the 200-year water surface. And so that way the water up to the 200-year would be passing down the rapids instead of across it. And then the last step, because once the pools are dug, the contractor can't get back in, was to excavate those resting pools in between the weirs and back out of the construction site. So here's an overlay of the 2 dams that were removed, and then same overlay with where that timber crib and the more modern dam were in relation to the completed rapids. This is a photo showing the building of the crest with that armor and chinking stone mix. This is the contractor building up the crest, but they've already built out the first 3 rows of boulders. They did leave this area open for equipment access, and so we weren't measuring or accepting anything on those sets of boulder weirs until they completed those and no longer needed to access from that corner. Walking through the steps here, so the contractor would build up that base made up of armor and chinking stone mix. That last little bit would be just that finer chinking stone to be able to push those boulders in to the constructed height. The boulders would be seated into that chinking material. And we did have a lot of tabletop boulders here that had flat surfaces, but there were some irregular ones that we put in as well. And so we just had to work with the contractor and make sure that we were getting very close to that design elevation with the boulder top. After those boulders are placed and we approve the elevation of the boulders, the contractor was then going in and placing that larger armor stone up against the boulder itself, and then backfilling with chinking to wash that in again to minimize seepage and potential scour right around the boulders. And so we were able to approve the elevation of the boulders, but we didn't actually sign off on the structure itself until we were able to measure that 0.6 foot head loss once the hydraulics once the water went through and the hydraulics were established. And to allow for that to happen, we did provide this to the contractor to show that top row of the ideal way of placing the boulders. If those are placed on an angle, they can then grab the boulder and kind of move it just a little bit back and forth to make sure that head loss requirement is being met. That also helps for fish passage too. If the fish are trying to move through just a shorter gap, the hydraulics aren't really going to matter for that 0.6 head loss, but it is a shorter path for the fish to go through. Whereas this bottom row, you could meet the 0.6 head loss requirement, but that's a much longer parallel flow path that the fish would have to move through. So there's a potential that you could have minimized fish passage success with the boulders being placed parallel to flow. So they worked from the upstream end to the downstream. This is something that I hadn't really thought about when I was drawing things on the computer, but one of the other reasons for that 2% slope across across the entire structure is to leave enough room for equipment in between each row of boulders, and the ability to go in and build the resting pools. So that's one reason to not increase the slope, is that there were certain weirs that were being built here where it was very tight for the contractor to get their equipment in. So like I mentioned, they had machine control and a GPS for confirming the elevation heights. So we would typically walk behind them, look at their screen, look at the cut fill, and if we were within 1/10 of a foot, we would approve that boulder placement and move on to the next one. And then after those boulders were placed, they were manually measuring those gaps. And then once the water was flowing fully through the rapids, that was when we would go through and look at this head loss requirement. So this is a profile showing a set of 6 different boulder weirs. This 0.6 target is what we're going for. And so in this example, there's too much head loss on the second boulder, but there is inadequate head loss, so there's not enough on boulder 3. And so in this case, what the contractor could do is actually open up the gaps at 3 to get the ideal 0.6 foot head loss that we were looking for. And then that would also help to back the water up to this excessive head loss here. In the lower example, we have a different issue. This would be inadequate head loss at weir 1. And then at weir 2, we have the excessive head loss. And then in this case, you could actually open up the gaps at weir 2, so that would let more water through. That would drop this upper water surface closer to the 0.6. And then in this case, you could start to fill in some of the gaps or adjust the boulder slightly to get the ideal head loss at boulder 2. So here's just some photos of how the pools were constructed and how the voids were sealed under each of the weir boulders. And this is what the constructed site profile looks like. So I just highlighted 1 row of boulders here and 1 row of resting pools, but that continues throughout the entire structure. Here's the normal pool elevation that the client was asking for. And then this is a 650-foot length at just over a 2% slope. Toward the bottom end here, we wanted to make sure we had the 0.6 head loss. So we had to add in a few weirs right at the bottom to make sure we didn't have a waterfall right at the end. So some of the challenges, very unconventional construction, unique materials. We did have very low flows during construction, so that was tricky to deal with. That subsurface flow, working in the river with making sure we didn't cause any turbidity issues, the head loss criteria, boulder placement. We did also have this hydraulic funnel that was happening, so the weir crest was 300 feet wide. Natural river width at the bottom end was 80 feet, so we had to make sure that we were actually stepping down appropriately for that narrowing of the channel. And then, like I just mentioned, kind of chasing that lower river slope. That was a challenge for sure. Successes, we were able to maintain our client's budget. We finished ahead of schedule, working with the local fish biologist. There was favorable review on their end and with their inspections. The contractor was great. They were awesome to work with. They were able to source most of the material on site. And we did have great community buy-in once the project got going. And there are 2 other rock rapid structures that are rock arch rapids that have been built in Michigan, but they do have a different design. They don't really use the sine wave. And also some of the gaps there are a little bit different than ours. So that's why I talk about this as the first design of its kind in Michigan. So for some of the future monitoring, this is very much in process, but we'd like to install some pressure transducers at the upstream and downstream end of the rapids so we can understand the head loss across the entire structure with high and low flows. We'd like to reinstall a gauge downstream of the rapids where there used to be an old USGS gauge so we can get measured discharge throughout the year. From there, we would do pit tagging on fish and install arrays for those pit tags at the lower and upper ends of the rapids. And then we could start to get a graph that looks like this. So this is from Luther's book. I had just doctored in this fake discharge, but you could see over the course of the year, what is the river discharge with those pit tags. During the survey, you can ID fish species. And so then you can see when certain species are moving through, whether it's a time of year or a discharge-driven movement. The other thing that pressure transducers can do is measure water temperature. And so we can really understand more about our fish being triggered by temperature. Is it discharge? Is it time of year? Is it all 3? Like this is all really interesting data, especially for warm water fish where we don't have as much information on them. And so we're working with Dr. Ashley Murky at Lake State. Jen Johnson with the DNR has also been very involved. But we also want to work with you because we need money. This is all voluntary. We are trying to go through the grant writing process. And if anybody has funding programs they've had success with for monitoring or ideas on how to build this research study, I would definitely like to talk with you more because this is kind of the new thing for me to think about now that construction is complete. So with that, I think we've got 10, 11 minutes. I'll let the highlight reel play and get to some of the questions.
Awesome. Great, Sam. This is very cool. I love that you figured out turning the boulders were going to make a difference. I've designed and built a couple of these, but I don't think I ever twisted the boulders like that. So I love that. Okay, well, let's get into some of these questions. There's a couple things that seem to be a little bit of a theme. First, there's a general question of is there a link to the report? And that was an early question, so I assume that's talking about the report early on.
Like our design report? Is that what?
I guess so.
Yeah. Well, in Michigan, all the permit applications are public. And so we have our permit application and the design reports embedded in there. Happy to share that, and that's accessible by anybody that has a MyEnviro account.
Yeah. Why don't we say if that's, yeah, you can get a hold of Sam, you can email him directly if
Sounds
you
good.
want, if you want a link to that. That's probably the best way. Okay, a couple questions on the modeling. I'm going to lump both of these together. You can answer them both together. What 2D software was used? And then another one, can you give more details on how the boulders were modeled in your 2D?
Yeah, so it's 2D HEC-RAS is what we used. And then I I guess, the civil 3D surface. We modeled with feature lines, top of boulder, bottom of boulder. Um, I actually didn't do the modeling on this, so I said I did everything, but that's not true. As far as model approach, I believe it was just that kind of mesh size I talked about, and then also just assigning a Manning's roughness value to that. I guess for the person asking the question, get a hold of me and I can put you in touch with the modelers that did this.
All right. So there's a little bit of a question on any reason to use chinking stone rather than rounded river stone. Concerns regarding scraping for fish during passage on sharp edge substrate.
Yeah, it's a good one. This is kind of the philosophical debate, right? Like as engineers, we like angular stuff because it locks in and we can sleep at night. But we are trying to build this into a natural system. So I don't have a fantastic answer on that, especially from the fish scraping side. I have gone in and snorkeled this a bunch since it's been built. I haven't scraped myself, but I do understand the question that there could be a conversation there. Maybe you do some thin veneer of smooth stone, where the fish is going to interact. You would have to upsize that because it's not going to lock in. But I do think it's extremely important to have the base not go anywhere. You don't want the foundation of your house going out from under it.
Yeah, and I will say this person did say chinking stone, right? So not the
Good
big
point.
boulders.
Yes. Yes.
But yeah, yeah, I think that worked. That still works on the idea. Okay, were in-stream restrictions waived by the agencies that September-November range?
Oh, yeah, like the kind of work windows. Yeah, they were. Yeah, so I'm not the biologist. I guess there would be some fall spawners in here. We did get a special exclusion to start the mussel survey early. In Michigan, you can't usually do the mussel survey until June 1st, but we did go in and snorkeled and saw that the mussels were already out and siphoning. I know the question was more related to the fall, but they were able to work fully through the fall, and I think they finished the first week in November.
Great. How flood resilient is the overall structure? Is it expected to change over time but still provide passage?
Mm. So the crest itself, like the upper end of the structure, um, we had to make sure we were below the 100-year because that's the regulated floodplain. We ran 200-year flows through there also. And so that intake canal that I was talking about that got filled, that's filled to a foot higher than the 200-year. With some of Luther's projects, he has had them in the ground, well, in the river, I suppose, for 20, 30 years. Um, we do get the question a lot of like, are the boulders going to move? How does the system look different? And you may have river sediments that are moving in and out, but the boulders themselves are not designed to be mobile. So as far as like this looking different in 10 years, we are passing high floods, and that is the design intent.
Right. Do you worry about sediment transport with the smaller stones in the rapids getting flushed out during large flows and the ponded water upstream being unable to replenish those stones?
Yeah, great one. That is something I've looked at when we've gone in and snorkeled. I mean, I'm not a sediment transport buff, but there's something to be said about I can't remember if it's called grouping or whatever, but like even though you have small pieces of rock, the fact that they're all laid in together, they kind of don't actually move that way. Um, I think the best answer there is to just continue to monitor it. Again, Luther didn't have a huge concern with it, and we did need to have some smaller stuff to fill in the voids. Um, but yeah, we'll have to keep an eye on it. This river does not have a very high sediment load, though. So we actually have the opposite problem of a lot of the sand bed systems. We will not have anything coming in to replenish. And even if we did, it would have to like fill the whole basin before it got to us. So we're kind of thinking of this as a hungry water sediment free discharge scenario with in respect to that.
Yeah. All right, I'm going to ask the two next questions back to back, I think you can probably answer both of them together. Have you found the shorter gaps effective to prevent debris accumulation that essentially looks like a bit of a funnel that could clog or points closed at upstream end? And then the second one is, do you anticipate maintenance issues with logs, trees, brush moving downstream and clogging up the boulder gaps? So questions around those gaps and clogging and how that may happen.
Yeah, and that is definitely one we have gotten a lot. I think the fastest way to answer the second question about just debris management in general is it would be no worse than the old dam was. And like no worse than anyone that was thinking about doing this at a dam site. So right now there are logs that have gotten hung up on the crest, but when the water comes up, that's going to float down and it might get hung up on the next set of boulders, but it's just going to move naturally the way that would move through a system if we hadn't built it. I don't have a great answer for the first one, the shorter gap part. That's really interesting. We've also gotten a question about ice and like basically you're going to lock the ice in, and I actually think the gaps help with that because ice is strong in compression but weak in tension. So the fact that there are gaps there, it allows for that to break up and flow through.
Yeah. Okay, this interesting. Is there an alternate term that could be used for the smaller rocks that lock in the designed larger boulders?
Yeah, I think we were kind of going for like the material in between logs on like a log cabin, that's called chinking material, but you could call it void filling. You could just call it like a generic name, 5-inch minus, and just talk about the purpose of it being to fill in the void spaces left in that armor stone.
Mm-hmm. All right. We are getting close here. We maybe can get one or two more in. It's kind of around debris as well. Concerns of beaver and the material they might add.
Haven't seen anything there yet. So yeah, I'll just say no, and we can move on.
All right. Were there any mine sediment tailings concerns or removal with the project?
Yeah, good one. So that mine is like seepage water that has gone in there into that old open pit mine. I guess we did not see any issues with reusing the waste rock. I mean, it has that larger density with having some metal content, but we did not do any additional testing on it, nor were we asked to. And so yeah, so far it seems there don't seem to be any issues there.
Yeah. All right, I'm going to ask this last question. If your question has not been asked, there's another 5 or so questions. Sam, are you up for getting those emailed to you? Those folks can send them out to you.
Yeah, absolutely. I guess, would you want me to like reply all so everybody can see it, or is it just to those individuals?
What I don't know that we have everybody's email address since we don't make people register for this. So I would say if folks email you specifically about it, just answer them.
Sounds great.
So here's the last one. Does this design improve habitat for mussel species or other non-fish species?
Excellent question. So we don't know. And I think with that last slide of like future research, that is absolutely a question that we would like to answer. So yeah, it's possible. And I do think for fish, a lot of fish are hanging out in here for habitat. This is not just a highway. This is not just for passage. There's a lot of reasons that fish would want to hang in the rapids. And that is why with the the pit arrays, we're trying to do that at the upstream and downstream end. Is if you have an array at the downstream end, they're hanging out in there for 3 weeks. They might just be loving it, but we don't actually know if it's a passage issue or if they're just using the rapids itself for habitat.
Yeah. Great. Well, this has been amazing, Sam. I'm glad you had more time to talk to us about this project. instead of 15 minutes. So
Yeah.
this has been really great. Thanks everyone for listening in. We've lost a few here at the end. People have to get the meetings and such, but this will be up on our YouTube channel, and feel free to share it around and listen to it again when you get the chance. Thanks again, Sam. Thanks everybody for listening in.
Yep. Thank you. See you guys.
Take care.